Hey everyone, it's Mr. Canfield. Today we are looking at the end of chapter 15, Taylor polynomials. We're going to talk about something called lagrange remainder. All right, so Stu tells us that a Taylor polynomial is an approximation technique. It has little value unless we have any idea how accurate it is. How good of an approximation is it? So if we use the variable r to represent the difference or the remainder between the function f and its Taylor polynomial approximation p sub n, we can state that the real function f of x is going to be equal to our approximation plus some remainder. We call r of n the Lagrange remainder, named after the 18th century mathematician. The Lagrange error is the absolute difference between the function and its Taylor polynomial. So basically it's saying, instead of calling it the remainder, we subtract the function and the approximation, and then we take the absolute value of it, and we call that the Lagrange error. And the idea is, it is at most that far away from the real answer. We know that our approximation is at most that far away. So, and the way that we find Lagrange remainder is we do a Taylor, and then we do one more term. The remainder is always going to be, it says f to the n plus 1th over n plus 1 factorial. Ignore the z for right now. X minus our center and n plus 1th. So like this is, it's just fancy notation to say, to get the next term in the Taylor series, and we're going to use that for a Lagrange remainder. So since Lagrange remainder is remainder is either positive or negative, the error though we take the absolute value, so we can talk about the error just being a distance. So z, the idea of z is we are not even going to find out what z is. This part here is saying, okay, if I plug something in here, what is, like z is like this arbitrary, we don't know what it is. And we're going to say, make z, who cares, so that this is as big as it gets. And we'll talk more about how that works in a couple minutes. The value of z is some number between x and c. We don't need to know what it is. So usually our, ones we've been doing, our center has been 0, and so if x was 1, then if we think about between 0 and 1, what's the greatest y value we get out when we plug in 0 to 1? Or the greatest output value. So I think if we do an example, that'll be the best way. So he does this. I think this is a decent way to think about it, with the TED and the loop and the stuff. So, all right. Oh, and he says down here at the bottom, there are two types of problems that we get on these. One is where they tell you what z is, like, hey, f of z is blah, 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 or z is this, or they will tell you, or it'll be easily determined. A lot of times with trig, like with a sine, what's the most sine ever gets to be? 1. So we just go, oh, well, let's say sine is 1. If it were as big as it could possibly be, here's what we would get. And that's the whole point of error of this remainder, is we're saying, well, hey, if we say on the next term, here's as big as the next term could possibly be, then that is how far away we could possibly be. Because remember, with each new term, we bring in more and more accuracy. So he says, also sorry for the steamy looking, like the fuzzy screen. I tried to fix my phone with super glue the other week, not thinking that the super glue would cover up the camera. And so I have some super glue left over on my camera. So, yep. They trust me to raise my children. Yep, that's a thing. Okay, so let's find the accuracy of the third degree Maclaurin polynomial for sine of 0.1. So if I want to find the Maclaurin polynomial, that is, third degree Maclaurin polynomial for sine of 0.1. So that's saying find a third degree Maclaurin and then plug in 0.1 to it, and that's going to be our approximation. And we want to find out how accurate that approximation is. So remember that when we do a Taylor-Maclaurin series, we start with the original function. So the original is sine, and then you just take successive derivatives, and you take that many derivatives. So f prime is cosine, f double prime is negative sine, f triple prime is negative cosine, and because I know what kind of problem we're doing a remainder problem, we actually want to go one more. So that's going to be what? Regular sine. And then we plug zeros into all these. So 0, 1, 0, negative 1. Okay, and we'll ignore this for now. So we'll write P3 of x. So that's going to be these coefficients, right? So 0, 1, 0, negative 1. And then naked x, x squared, x cubed, and then over nothing, over 1, over 2 factorial, over 3 factorial. Okay, let's clean this up. You're gone because of the zeros. And let's see, 3 factorial is 6. So the P3 is 1x, so x minus, you could say 1/6, or you could say x cubed over 6. So that's our P3. So if we want to find Lagrange remainder, oh wait, no, we got to plug in 0.1. So if I plug in 0.1 to this, let's see, 0.1 cubed, that's 1 times 1 times, it's just 1, but then we're going to move the decimal place 3 times because there's 3 numbers behind the decimal in the multiplication. So, how many do that divided by 6? Oh, shoot. Let me grab my calculator. So for me, the way I was going to get this by hand was doing something silly with a fraction, and we don't need to worry about that. Okay, so we got 0.09983. It looks like this is 3 repeating after that, but 1, 2, 3, 4, 5, 6. Okay, so we got that. And what we want to find out is how far is this from the real function? Yes, we could plug in sine of 0.1 and we could find out what the real function is, but that's not the point. The point is, without knowing what the real function is here, we can still know how close this is to the real thing. And the way that we do that is we use the next derivative. So I'm going to use this, and we're going to get a number. I guess I should circle it. We're going to get some number here. And that's going to go, well, think about how that would look in the next part, right? So in the next part, it would be this number times x to the 4th over 4 factorial, right? So what is this number? And what Lagrange error says is, instead of finding out what this is, like in the actual, I'll plug in 0 and get something, what's the biggest this could ever be? The biggest sine is ever going to be is 1. So I could replace this with a 1, and I know there's no way it's going to be bigger than that. What we're trying to do is we're trying to say, okay, I got this number. If I get off by however much this is, I'm guaranteed this is going to overshoot where the answer actually is. It's either going to overshoot or hit the actual answer, I should have said. So let me use this to overshoot. Well, I'll plug in 0.1 to this. 4 factorial is 24, I believe. So I got 4.1666 repeating forever times 10 to the -6th. So that is move the decimal place left 6 times. So that's 1, 2, 3, 4, 5, 6. So 0.000004116 repeating, or 417. This is the biggest the next term could possibly be, which means we have this, and to get to the real function, we have to go this and as much as that. This is our error, our Lagrange error. So let me see if So if we wanted to talk about the possible values of sine of 0.1, we could say that sine of 0.1 is less than or equal to, I'll call this A and I'll call this R. That, like, instead of writing the whole decimal, this A number, if I take that A number and I add our remainder onto it, if I add those together, that is the biggest sine of 0.1 could possibly be. And then if I take A and subtract R from it, that's the smallest it can possibly be. And so we know sine of 0.1 is going to be wedged somewhere between these two values. So I'll take this, I'm going to store this as R, because I can do that in my calculator for fun, and take this other one that we got. I'm going to store that as A. So if I take A plus R, I get 0.099835. That is the biggest that sine of 0.1 can be. The smallest it could be, A minus R, is 0.0998291666. So if you look here, so 0.0998, it's either 0.09982 or 0.09983. That's the level of accuracy that we know we have. It's somewhere between those two values. And so if I now go and have my calculator calculate full decimal accuracy here, I get off the screen, all right? I get 0.09983 and then 341. This says 75 something. So this is slightly less than that, which is what we said was going to happen. So it's mind-boggling how accurate that is. Like, that's super. We're dealing with such a minute difference at that point. But yeah, that's Lagrange remainder. We'll do one more of these. I think for this, the concept is challenging, but the actual mechanics of it are easy. You go one more step, and then you figure out what that is, and that's how far you could be off by. So we want the largest possible value for 1 over root e using f of x is equal to e to the x. What would I have to plug into x to turn it into 1 over root e? That's going to be important to us in a minute. Well, 1 over root e is e to the negative 1/2 power. So that means I plugged in negative 1/2 for x. That's going to be important to us later. So we're going to see this kind of stuff written, and it's a way of them asking us, hey, what's f of negative 1/2 of this function? They just kind of bury the lead a little bit and hide it from us. So they want us to use the 4th degree. Oh, and we're using e to the x. What a wonderful, because e to the x is e to the x all the way down. And we're looking between, oh, right, we want negative 1/2, or they use negative 0.5. So our center is 0, and the x value we care about is negative 1/2. And so, all right, I'm getting ahead of myself a little bit. 1, 1, 1, 1, these are 1s all the way down. So if I'm doing 4th degree, that's going to be 1 x squared, x cubed, x to the 4th, over nothing, over 1. Oh, it's over 0 factorial, but it's 1. So 1, 1, 2 factorial, 3 factorial, 4 factorial, plus, 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 plus. Okay, here's our polynomial. I can plug in negative 0.5 to that. The way I'm going to do it is I'm going to say negative 0.5 store x, and then I'm going to say 1 plus x squared over 2 factorial is just 2, plus x to the 3 over 3 factorial is 6, plus x to the 4 over 4 factorial, which is 24. Okay, so I got 0.606770833 for my p sub 4 of negative 0.5. Okay, so that's our p sub 4. That means to find Lagrange remainder, we will go one more term. We got our x to the 5th over 5 factorial, and what's the most this is going to be from negative 1/2 to 0? And if you remember what e to the x looks like, e to the x is like this. The further left you go, the smaller it gets. The further right you go, the bigger it gets. So between negative 1/2 and 0, 0 is going to be the biggest, and it just gives us a value of 1. So a lot of times it'll be 1 for these kinds of problems. And so I can plug in that negative 0.5 to this now to find what the next term could possibly be, the biggest the next term could possibly be. And so I'll just say, oh, that's the same, that's just the x value I had already plugged into my calculator. So I can say x to the 5th over 5 factorial, which I've memorized as 120. So that is 0.0002604166667. I like writing the zeros, and you can write it like that. It doesn't matter, and it's a negative. Okay. So the idea is you take this, and we're going to take absolute value. This is my remainder, right? So we're going to add or subtract this onto that, and that'll give us the range of possible values. So this is our error. That's how much we're off by. Okay. So I hope this was helpful. Finishing out our introduction to Taylor and Maclaurin series. These are your friend for this. Just type in numbers in. Again, the actual process here is really easy. You go, you do the Taylor and Maclaurin like you're used to. You do one more term after that, and you make up that number. A lot of times it's 1. Yeah, there you go. Hope this was helpful. Have a good one. Bye.